In this video, we're going to look at determinants and Cramer's rule for a 2x2 matrix. So, to begin, we'll look at how to find the determinant of a 2x2 matrix. Consider the 2x2 matrix A given by A, B, C, D. Then the determinant, which could be expressed like this, so vertical bar A, vertical bar, or the determinant of A is equal to, and notice the difference in notation here. What we see here is actually a vertical bar, not the left bracket. So this might be another notation that you'd see. You would see a vertical bar and then the entries of the matrix finishing with another vertical bar. We should distinguish that from the actual matrix A, B, C, D. Okay. So whenever you see a vertical bar and then what looks like matrix entries, that's actually indicating find the determinant. And the way you would do that is you would first multiply the entries of the first diagonal, so AD, minus BC. Okay. And we might recognize this from part of the formula to find the inverse of a 2x2 matrix. Let's see our first example of how to find the determinant of a 2x2 matrix. In this example, we have our matrix A is 1, 2, negative 2, 1. So we could express that we're finding the determinant by writing it like this. Equivalently, determinant of A, or finally, okay. And here the vertical bars indicate that we're taking the determinant of this. So we would find the determinant by saying 1 times 1 minus negative 2 times 2. Okay, so negative 2 times 2. Simplify this expression and we'll get 1 minus negative 4. 1 minus negative 4 equivalent to 1 plus 4. And we get the determinant of A is 5. Now let's look at an example. So apply these skills to the matrix B. So I recommend you pause this video, find the determinant using the formulas that we just talked about in the last few seconds of this video. Once you've found your determinant, unpause and you'll see the solution and you can verify your work. After finding the determinant, we get the value that the determinant of B is 6 in this example. Now we're going to use what we just learned about the determinant of a 2x2 matrix and apply this to be able to find the solution to a system of equations, a system of linear equations. So we'd have 2 equations and 2 variables using determinants. Okay. So to begin, we start with the first equation a1 times x plus b1 times y equals c1. Here a1 is the coefficient in front of the x, b1 is the coefficient in front of the y, and the subscripts are just indicating this is for the first equation, just to help us keep straight everything later on. The second equation, a2 times x plus b2 times y equals c2. Again, just note the consistency among the subscripts. Now what Kramer's rule does is if we were able to solve the system of equations, we know the final answer would be something like x equals a number, y equals some other number, possibly the same, depends. So we'd be looking for the value of x and the value of y that is a solution to the system of equation. What Kramer's rule tells us is that you can find the value of x by looking at this expression. Now let's take this piece at a time and explain what it is. To begin, we'll start with the expression on the bottom just because it's most familiar to us. We notice this is just D, and here D represents the determinant of the following matrix. So D is the determinant of the matrix A1, B1. Okay, the coefficient of the x of the first equation, coefficient of the y of the first equation, A2, B2, coefficient of the x of the second equation, coefficient of the y of the second equation. And we know the determinant would be A1 times B2 minus A2 times B1. So that's what this D is. And see that D is here, and here. So this is how to find the value of y. But we'll finish that. So you would find the determinant, and it would take the place here and here. Now this D subscript x is represented as the determinant of this matrix. Let's look at our original determinant. A1, A2 is the first column, B1, B2 of the second column, and notice what has changed here. While the second columns remain the same, in both cases we have B1, B2 is the second column here. Okay. Do we see that the first column has changed? Instead of A1, A2, which is the original first column, we have replaced that with C1, C2. And C1 and C2 are actually the coefficients of what the first equation is equal to and what the second equation is equal to. So D subscript x, dx, you find it by replacing the first column with what the equations are equal to, first equation, second equation. Calculate this determinant, which would be C1 times B2 minus C2 times B1. And then this is a number, divide them, and that's actually going to be the solution, the value that x would have to be a solution to this system of equations. And I should note that this holds so long as the determinant D, determinant of this matrix, is not equal to 0. So now let's turn our attention to how would we find the value of y that is the solution to the system of equations. So y is going to be equal to D sub y divided by D. We already talked about this D, it's the determinant, which we can find by looking at here, written here. And then D sub y is kind of has some symmetry to D sub x. Notice in this case we're looking for the value of y, so we have D sub y. And what we notice is the determinants that we're calculating are similar, except for now in this case, what would generally represent the coefficients for the y, the second column, now no longer are they B1 and B2, they're now C1 and C2, which we know are the values that each of the equations are equal to. You would calculate this determinant, A1 times C2 minus A2 times C1, some number divided by some other number, and that would be the value of y. So just by finding the value of three different determinants, this is different, but these are the same, and then applying the correct formula, we would quickly get the solution to the system of equations, x equals y equals. Let's apply this to the problem below. We're asked to solve this system of equations using Kramer's rule. We would first write this as a matrix. So we'd write it as a matrix here. So coefficient of the first equation, coefficient for the x is 1. First equation, coefficient for the y is 2, equals negative 11, similarly below. And if we want to use Kramer's rule, we know that we're going to need to find these three matrices. We're going to need to find D. We need to find the determinant D sub y, and then we need to find the determinant D sub x. So let's begin by just finding the determinant D. Okay. We know the determinant D will be equal to the determinant of this matrix. Okay. A 1 times 1 minus negative 2 times 2 okay. So D is 5. Next, if we want to find the value of x first, we know that's going to be equal to D sub x divided by D, which we could replace. We already know that's the value of 5. Okay. So off to the side we would find D sub x, which is the determinant. Since we're trying to find the x value, D sub x, we would replace the first column with this. So we would say negative 11, negative 13 replaces the x column. Y column is left alone, so we'd have 2, 1. We would find this determinant, negative 11 times 1 minus negative 13 times 2. So we get that d sub x equals 15. Okay. So we would complete this formula. So x is then equal to 15 divided by 5, which would have the value of 3. So x is equal to 3. Next, we need to find y, which we know is d sub y divided by d. We already know the value of d remains as we found before, 5. Why don't you take a moment to pause this video and attempt to find d sub y. Unpause and we'll see the solution. So after finding d sub y, we should get the value of d sub y is negative 35. Finishing our expression, y equals d sub y divided by d. So we get negative 35 divided by 5. So our value for y is negative 7. So x equals 3, y equals negative 7 is the solution to our original systems of equations. And remember, you can always check your work by substituting the solution into both equations and making sure that it works in both equations. Let's do that. Let's check our work. So substituting the values into both equations, we get for the first equation, it does indeed equal 11. The second equation, when substituted in the values correctly, we do indeed get negative 13.